session on carbon footprint management. We have 4 participants and I would like to introduce them. Kapil Batra, managers from Engineers India Limited. Then Iram Maimuna, CEO, US Private Social. Then Vishal Vij, Head-Renewables from Tata Power. And our 4th participant is Sumitra Ghosh, Principal Heat Transfer Engineer, Shell India Marketers Private Limited. So I wish them all the best for their presentations and I request Kapil Batra to go ahead with his presentation, please.
So my name is Kapil Batra. I come from the hot city of Nagpur, and I've worked with high temperature fired heaters for the past long time. So I am very comfortable with the hot heaters. I hope to make you understand and make comfortable with the heaters. Okay. Good morning, ma'am. Good morning, all my colleagues. A very warm welcome to all of you to this session. So my topic is hot in more than one ways, if you see. First is fired heaters have a very high temperatures. Second, I'm going to talk about alternate fuel firing, electrification, and efficiency maximization. So these are all the buzzwords or the hot topics in today's discussion. So why do we talk about fired heaters, right? Why is there so much fuss around fired heaters? So as we have heard in the previous sessions, a lot of sessions, that India is trying to double its energy capacity or the refining capacity by 2030. And at the same time, we are trying to drastically reduce our carbon emissions. Right? We have set a very bold targets for reducing carbon emissions. And when we go for reducing carbon emissions, and if we look around the refineries, right, there's one hotspot or the one shining star, and that is fired heaters, responsible for 60%, more than 60% of carbon emissions only through combustions of conventional fuels like RLNG, natural gas, right? What happens is they contain carbon, these fuels contain carbon, and when they combine with oxygen, they form carbon dioxide, right? So they are the major hotspot. And before going into presentation, let's set us an impact scale, right? For a 10 TPA refinery, right? I've considered a 10 TPA refinery. It could be extrapolated for others. The total carbon emissions is around 1 million tons per annum via fired heaters through combustion. And the India's refining capacity existing is around 250 MMTPA. So just multiply by that number, and there are huge emissions, right? So it will turn the greenest of activists red, like why fired heaters are emitting so much carbon emission. Efficiency standards, right? So let's get cozy with fired heaters, understands what are fired heaters. So fired heaters are generally designed for 80 to 93% of efficiency. So what is efficiency? I have an absorbed duty divided by the fired duty. So to give you an example, if I had a duty requirement of 9 MMBTU, I am firing 10 MMBTU of fuel. So it's like 0.9, 90% of efficiency is for this system, right? So currently fired heaters, depending upon various considerations, are generally designed for 80 to 93% efficiency. Moving on to, I've set the scale, why we require decarbonization of fired heaters, right? It's as clear as the Goa skies that we do need decarbonization of fired heaters. So the strategic focus of my presentation is, first is the efficiency maximization. We'll look at what is the current constraints with designing fired heaters, what is the best possible efficiency with conventional fuels like carbon fuels, and then we will move on to pivoting through the alternate fuels like renewables, not renewables exactly, but fuels with low carbon content like hydrogen fuel. So when hydrogen combusts, it's like hydrogen plus oxygen gives you H2O. There is no carbon content. So if I'm mixing 50% conventional fuel plus 50% hydrogen, that much carbon dioxide emissions will reduce. And the last part would be, why not electrify fire heaters, right? That's our the buzzword, like let's use green energy and electrify the fire heaters as well. So let's take a brief look at the energy requirements in a refinery. So the energy requirements, let me allow you to show a pie chart. If you see, this is the distribution among fired heaters in a refinery, right? And if you say about 1600 MMBTU per hour of firing rate is required in a 10 MMTPA refinery, and you can extrapolate based on your refinery requirements. So it's very clear that the energy hog is the CDU-VD unit consuming around 40% of emissions, right? And energy consumptions but linearly relate to your emissions. So even if now if you see 1600 MMBTU per hour of firing rate, this is considering 91% efficiency in a refinery, right? And 91% of efficiency in refinery. And if I consider a fuel cost of $11 per MMBTU, even if I save 1% in efficiency, I move from 91% to 92%, the cost savings would be huge, humongous, $1.5 million, approximately in only fuel expenses. And I'm not considering any carbon cost right now. That would be covered in the next slide. And if you see the eco gains or the carbon gains, we have slashed it by 1%. So 1 million we were emitting in 10 MMPTPA. So even if I say 1%, it's 10,000 tons per annum are reduced carbon emissions. Hope I am not going very fast. And the economic impact, if we consider a hypothetical situation and a carbon pricing of around $50 per ton of CO, $50 per ton for CO2, 11 USD per MMBTU of the fuel cost, which I've considered in my entire presentation. So I've considered the baseline. Now this graph, let me just quickly tell you. On the left-hand side, you have the economic impact per MMBTU for 1 year of operation. And the bottom is the efficiency, the baseline efficiency. So using this chart for any absorbed duty or the fired duty, you can multiply by the difference and you can get the amount of cost you will be saving. So these are baseline efficiency is 91%. The enhanced efficiency, I've improved it by 2%, that is 93%. So the total impact is 4.1 million USD for a 10 MMTPA refinery. So I have multiplied this by 1600 MMBTU per hour. Okay, so and from this you can infer that 20% of cost is by saving the carbon emissions. So since we have set the stage, now let's look at how we design a fired heater or what are the constraints. So a simple fired heater, if you see, is an all radiant heater, the basic fired heater. It's used for low pressure drop applications and even for very low duty requirements. So it's very economic at this temperature to go only for the radiant firing, right? If I want to improve the efficiency, what I will do is, on the top of this radiant section, I would put a convection section. Then at this flue gas exit temperature, I will be able to increase the heater efficiency to 80 to 85%. And the constraint over here is the process inlet temperature. So as your process inlet temperature increases, your difference between the flue gas exit temperature decreases, right? So you require more area and that becomes the constraint. And we have also option of waste heat recovery like steam generation, steam boilers. So the BFW inlet temperature is less, so we can decrease the flue gas exit temperature. So the efficiency increases to around 90%. And when we have exhausted these options, we go with the cast air preheater system. So what cast air preheater system does is, it takes the flue gases and reduces the flue gas temperature by preheating the air. So the only constraint with cast air preheaters is the flue gas acid dew point condensation. So in the flue gases, there is a term called flue gas acid dew point condensation. So if you're cooling the flue gases further, the acid condenses on the tubes and it corrodes the tube. And also in the downstream equipment, there will be a problem, right? So there is a limit to where you can cool the flue gases and that impacts your efficiency directly. And to solve that issue, we have a steam air preheater. So what we do is we preheat the air so that we do not have cold spots in the cast air preheater and we can reduce the flue gases further. So that here we arrive at 150 degrees C of flue gas exit temperature, that is 93% efficiency. So this is what is provided generally in most refineries. So if you see, we are losing around 7% of 7% of heat to the atmosphere. And the advancement or the latest development that we have up our sleeves is the acid resistant air preheaters. What these air preheaters do is they allow the flue gases to condense in the air preheater itself. So as the flue gases condense in a polymeric APH, their dew point is reduced. So you can use the other equipments as it is. There's no need to change the other equipments, and you will be able to use the same equipment. So we can cool the flue gases further down to reported references with these air preheater vendors are around 95 degrees C or 100 degrees C with a payback of around 5 years. Since, as I explained, the acid dew point is lowered, the downstream equipment is protected. Then we move on, like once we have the best possible efficiency, best design with the conventional fuels, the only option left with us with low carbon content firing. So when we go with low carbon content, as you see from the slide, the fuel oil is 100% emission. I've considered for this presentation, 100% is through fuel oil firing. And when we go with hydrogen rich firing, around 80-20% split, if you can see the carbon emissions, which are in orange, are reduced drastically, right? But all is not sunshine, right? The hydrogen firing comes with its own challenges. Hydrogen has its own unique properties, as you can see in the slide. So the major advantage with hydrogen fuel, as a fuel is it has a very high calorific value. There is no carbon emission. Hydrogen burns as H2O. H2O, it forms only H2O. It has very high adiabatic flame temperature. So when it has a high adiabatic flame temperature, it is a 2H watt. Adiabatic flame temperature helps you to improve the radiant efficiency, but it also increases the NOx emissions. So once you decrease the carbon emission, but you increase the NOx emissions, which will be highlighted in the further slides. And coming to the issues with hydrogen firing is hydrogen as a molecule is very light, very low molecular weight. It is more prone to leakage, and it has a very low ignition temperature. So low ignition temperature is good for combustion, but when you want to prevent from combustion, it's difficult, right? So the equipment has to be designed for more safety when you are firing hydrogen. Emission impact, as we discussed, completely eliminate carbon. And the NOx concern is that, as we will see in the further slides, that with respect to the conventional fuels, such as natural gas, hydrogen is a significantly high adiabatic flame temperature, which drastically increases the NOx emissions. Efficiency gain, for a natural draft heater, we can have high radiant section efficiency, and it can improve the it can improve the overall heater efficiency by around 2%. And even for a forced draft units, if we have a clean hydrogen fuel, we can lower the flue gases further, right from 150 degrees C, as we seen in the previous slide, to around 120 or 125 degrees C, and we can have that substantial gain in efficiency. So equipment adaptations, hydrogen being a very light fuel, it has comparatively high volume compared to your natural gas or the conventional fuel. So the fuel injectors needs major changes. And other considerations, as I talked about, are the fuel, air and delivery system. Flame detection is a problem because when you have carbon on the pilots, the flame detection work. But when you don't have a carbon, the mechanism has to change from what is traditionally used. So you can see in this slide, I have compared different composition, like consider 100% methane firing, then 50% hydrogen, 50% methane, and 10% methane, and 90% hydrogen. So you can see there is a drastic reduction in carbon emissions, but there is also a significant increase in the NOx emissions. So the burner has to be selected such that the NOx emissions are not increased. So burner vendors are definitely improving the burner model to reduce the NOx emissions drastically. Why not we electrify our fired heaters using the green electricity, right? There's a global push towards electrification. So there's a strategic focus worldwide for electrification. And if you see the cost in this chart, pie chart, if you see the cost of electricity, which is indicated in the green, is very high compared to the fuel gas firing, even along with carbon credits. So there is one more thing, one more challenge with electrification is it has a very huge demand on electricity. So 400 to 500 megawatt for a 10 mmTPA refinery. Imagine for a 250 mmTPA refining capacity of India, how much would be the electric demand? And then renewable electricity, which is the green electricity, is also weather-based and it's not available throughout the time. Other thing, as you can see from the presentation, the pie chart, the cost is very high. Even if I am considering the electricity cost at 6 rupees per unit, and if we can reduce the cost to 3 rupees per unit, this difference in cost of the operating cost will come to around 20%, right? But still, if we see the capex, this is just the operating cost. So capex will also be higher. So all this needs to be accounted for, and I've also considered a very conservative estimate for the carbon emissions, like $50 per ton. We do not have any scenario in India, but this is what is the estimated time, right? So a few challenges with electrification, and it also has its own sunshine points or the advantages. So the advantages are the space efficiency. Once you have an electric heater, right, you will not need a cast air heater, FD fan, ID fan. So it saves substantially in cost. Got it. Just a minute, just a minute. And even the heat distribution is uniform from the technical point of view. It offers precise control. The holistic cost consideration, if we go for, can be beneficial as the technology advances, cost reduces for electricity, and we have better infrastructure. So these are the two types of electric heaters that we have at present. This is the immersion type, which has been in the industry for a long, and slowly a very complex heaters like ethylene cracking has been done with the electric resisting heating, right? So this is the upcoming technologies that we have in electrification. To summarize, we need to focus on efficiency. We have to go for the alternate fuel firing, and also as we progress with the technology, we'll have to adapt to electrification to meet the needs of refining as well as carbon reduction. Thank you, everyone. And I would also like to thank contributors to this presentation.
Thank you,
Thank you.
Kapil, for excellent presentation. So, may I now request Iram Maimuna, CEO West US Socials, to go ahead with her presentation.
Good morning, everyone. Respected chair, fellow delegates, and fellow speakers. Uh, and I'll give a quick introduction about myself. My name is Iram, and I am the co-founder for eWaste Social. We are a B2B auction platform where we connect companies generating recyclable waste directly to registered recyclers, thereby ensuring that the waste gets recycled appropriately and also tracking the carbon emissions and the life cycle of the waste. So that's what I do. Uh, we our operations are pan India, and and today we'll be talking about the framework for assessing the environmental impact of electronic waste recycling by using standardized metrics for energy efficiency. So we all know about the e-waste that we are generating. Electronic So we all know about the e-waste search and the triple challenges that the companies are faced with for energy transition, decarbonization, and sustainability. We also need robust methodologies to measure the e-waste recycling impact. We need to align these e-waste recycling efforts with broader sustainable practices. Collaboration, again, focus from all stakeholders, including responsible production as well as responsible consumption. We need to create awareness and education and policy advocacy through central and the state government. So we all know the quantum of electronic waste generated in our country and across the globe, and out of which only 7 to 8% gets recycled in a formal manner, and rest 20 to 22% gets recycled in the informal manner, and rest 70% ends up in the landfill or in is not the material is not recovered appropriately from it. So that is the quantum of waste from where materials can be recovered and energy can be reserved. We are sitting on. So why energy efficiency in recycling? uh, if you would see, a lot of carbon cycle include natural or technological processes involving either CO2 emissions or carbon as a raw material. The processes manage and potentially reduce carbon emissions into atmosphere in three distinctly different ways. Reuse, increasing recycling or reuse of carbon feedstock in products and processes. Removal, CO2 sequestration by the way of natural processes. Storage via direct air capture of carbon or carbon storage products. The focus on sustainable biomass and carbon capture in recycling technologies can lead to more energy efficient processes. And in following slide, we'll talk about how we can do that. So promoting energy efficiency and sustainable carbon strategies for circular economy and environmental conservation. Here we talk about that most of the carbon supply comes from biomass, agriculture and forestry, and only 1.5% coming in from the recycling. So thereby, by increasing the recycling rate and also the uh, energy saving mechanism in the recycling technology, we can ensure higher carbon supply from the recycling process. And that's why recycling is so important. Also, it reduces the greenhouse gas reduction by ensuring circular practices, and emphasis on sustainable biomass and carbon capture also contributes to the environmental benefits. Again, it also saves landfill space, saves environmental resources, reduces environmental hazards, energy conservation, resource recovery, create employment opportunities, affordability, reduce the impact of global warming. So here we talk about the different types of e-waste recycling. We have hydrometallurgy method, pyrometallurgy method, biometallurgy method, and traditional treatment method. And I will take you to the next slide of why it is important to understand the types of e-waste recycling, because that is directly linked to the energy consumption. So in energy consumption in different e-waste recycling processes, if you see the traditional treatment method of disassembly, shredding, sorting, refining, and disposal, the energy consumption varies. There is no fixed parameter as to how we can record the energy, or how we can know, how much energy was consumed, or how much was recovered, and how much could be saved, depending upon the types of machinery and the capabilities of the workmen. The energy consumption varies. If you look at the pyrometallurgy method, which include pre-treatment, pyrolysis, melting, and refining, energy consumption is significantly high because of the mechanism used in this entire process. Hydrometallurgy method also include shredding and sorting, leaching, separation, purification, and recovery, and it consumes higher energy. And in these sort of systems, or in these type of processes, there is a possibility of reducing the energy consumption, and recovery can be also made higher, because we know that there's already high consumption of energy being used. Then there is biometallurgy method. Again, it reduces bioleaching and bio absorption, and the energy consumption is lower, but the cost is high. Again, the entire process also depends upon the cost, because a lot of times the cost savings are done in the form of using high energy machines, which are probably older technology, and thereby the recycling sector is faced by multiple challenges for energy consumption and saving. So how do we measure the recycling energy efficiency impact? We have the environment parameters, carbon footprint, energy and water usage, waste generated, and collection, biodiversity impact, etc. We have the social parameters, employment generation, health education, community engagement, to ensure that women and should not be working in those uh, segregating sites, because a lot of times we have seen that when women work in those sites, they end up getting their children and exposing them to harmful chemicals and toxins from the electronic waste. Again, then we have the economic parameters, cost saving, revenue generation, ROI, and the market value. And the impact assessment frameworks are by the UN SDG, IRIS, IMP's 5-dimension, LCA, and SROI. Uh, so all these gives us a holistic impact measurement, and it is crucial for making informed decisions and accountability in sustainable development, and also using technology advancement in recycling processes. So when we know that, okay, this process is being used for a certain recycling for recycling a certain e-waste, we know how energy efficient, or how how much energy it is consuming. So we use for four-step framework, where we help have a multi-dimensional approach, incorporating various metrics like carbon emission reduction, energy saving, resource recovery, and transportation impact. So by transportation impact, we are promoting local recycling, thereby ensuring that the waste gets connected to the closest recycler. And the companies also will get the information about the quantifier of the carbon emission saved, energy conserved, recovery of material, cost benefit achieved through recycling activities, and transportation of the impact. So these are the overview of the environmental impact, and again we talk about the carbon emission reduction, energy saving by different processes, transportation impact also also includes if the waste was transported through a diesel versus a CNG versus an EV vehicle. Um, Waste life cycle analysis, material life cycle analysis, recycling versus landfill on incineration, cost savings, and the landfill space saving. Again, if you minimizing the use of landfill space through effective waste management. And toxic substances mitigated. Any electronic waste consists of various toxic substances, and to mitigate these toxic substances from the environment is another way we measure the impact that you can create by efficient recycling. So this is the methodology of impact measurement that we have taken. Where conducting a local e-waste recycling auction involves selling 250 kgs of mixed e-waste to a recycler using a traditional method, and so the total CO2 avoided by local recycling is 82.5 kg. Energy recovery by non-recyclable is 2.475, and for local recycling is 265. So we see the impact of the local recycling over here higher, but the process used is traditional, so thereby the energy consumption is also lower. Here again, we look at the impact measurement of item-wise. We take different materials like a fridge, laptop, printer, air conditioner, mobile phone, and what is the impact and the total CO2 reduced if we are able to recycle within 50 kilometers. Again, we need to ensure that our state has enough recycling facility, and they are sustainable for them to be operational, because a lot of times either they won't get waste, or they will not be sustainable enough to be in practice. So this, so again, the metrics used for each of these case studies have been different, because the type of material and the energy consumption varies depending upon if I'm recycling a laptop versus a printer or a mixed e-waste. So these multiple framework and measurement features vary the energy consumption and also the carbon impact on the environment. Here we are taking a recycling of 1 ton of laptop waste, and this is the CO2 saving and energy saving, and also the carbon footprint reduction is 1240 kg. Again, we have in all parameters we have kept the process of local recycling, and ensure that we are recycling within 50 kilometers, and not that the e-waste is transporting from more than 50 kilometers. So why again I'm insisting on local recycling in 50 kilometers, because a lot of times our waste gets transported from one city to another, and also from one state to another, and one country to another. So the transportation incurs a huge impact of carbon footprint on the environment, and thereby by ensuring just one measure or one aspect of local recycling, we can reduce emissions drastically. Here is the environment impact report of 1 ton of laptop waste, where the metal recovery has been close to 700 kgs, plastic around 200 kgs, and glass around 100 kgs. This also includes a little bit, 5 to 6% of waste which cannot be recycled. Here we are aligned with the frameworks of SDG 12 of responsible consumption, because once the waste is generated, it is in the hand of the consumer who has the material to recycle it. The greenhouse gas emissions, 1290 kg equivalent. Here we are focusing on SDG 13 climate action and IRIS and P19260. The local economic benefits are close to zero point 0.5 full-time jobs created per kg, and 200. So this is per kg, and SDG 8 of decent work. Again, creating that advocacy and creating that cre- uh, creating that awareness that decent work situation should be done. Social benefits, again, skill development, community engagement, and local environmental benefit and energy savings. Again, this is a similar one for 1 ton of printers, but it varies from laptop, because the material recovery, again, for printers, why I took this case study was because printers vary depending upon uh, the year in which they were manufactured. A 2011 printer would fetch me more metal or more precious metals than a 2020, because now we are designing a lot of our products are designed to dump, not to reuse or refurbish it. Hence, the every product, it varies the energy impact and the carbon footprint impact. So we have taken a simple methodology and various metrics in order to come to this conclusion of the previous slide, and it includes how it was collected, sorted, material recovery, environmental impact assessment, energy saving. Again. Depending upon the type of recycling used and what in what facility are we doing it. So in the concluding slide, I would like to focus that we need to optimize the processes, the recycling processes, and in order to make it more sustainable, we need to ensure that we have local recycling facilities available in every state and city. We need to ensure a comprehensive view of energy efficiency, addressing resource utilization, emissions, and renewable energy. Embracing these metrics reinforces environmental responsibility in e-waste recycling. Improved energy efficiency can lead to cost savings and economic sustainability, because any recycling to be appropriate, it needs to be sustainable. And we need to be able to enforce data driven decision making, and through these frameworks, we can help companies achieve that. And consistent monitoring supports long term sustainability goal in this sector. Thank you.
Thank you,
Yeah,
Iram.
thank you.
Next speaker is Vishal Vij from Tata Powers.
Good morning, everyone. So I am Vishal Vij. I am from Tata Power Trading Company Limited, to be precise. So we are the 100% subsidiary of Tata Power. We are dealing into the energy trading and the power trading of it. So I have been grateful to be in this presentation. I have heard the presentation given by Kapil and ma'am. So the perspective which has been discussed up till now is how to decarbonize or reduce the carbon footprints. So why is this perspective gathering momentum in India? So we will be talking about it and how we can actually price or put a valuation to the carbon footprints which are getting reduced. And prima facie, what I heard the investment is the major challenge in rolling out of any new technology. So this is a brief overview. This is about Tata Power Trading. This is what we do, but I will get onto this. So our topic is monetization of the latent emissions. So like Kapil was mentioning that once you are doing such kind of efficiency measures and you are able to reduce the carbon footprints, and you had taken a certain quantification of the carbon credits to make the entire investment viable, right? Now what is the certain requirement which has gathered interest within the technology, sectors and the renewable and the oil and gas sector is that there is a huge thrust from the Indian government. They have entered into a Paris agreement, and they have a nationally determined contribution which they have to meet net zero compliances by 2070. So BEE, Bureau of Energy Efficiency, has also rolled out an Energy Conservation Act, under which certain different sectors have been covered. And I don't know, gradually it might happen that the cost of compliance might make the technology rollout more efficiently and it more viable. So I'm just going to talk about what are the drivers basically which are instigating this, you know, need for carbon footprint management. So there is a lot of investors demands in new startups. If you say the data centers, if you say the technology partners, so if you say the green investments which are flowing in India, they have in the mobility sector also, they have a certain requirement that you have to reduce your scope 1, scope 2 and scope 3 emissions, come what may. So this is also being driven by the consumer awareness and the new consumer base. I mean, I can say the new technology which are getting rolled out, and for that the new consumer base which is coming up. So the e-mobility, the e-waste handling thing which you were mentioning was also a very enlightening subject. So it is not yet being covered by any regulatory framework, but this is a very noble cause. I mean, if we are able to reduce the carbon footprints and generate carbon credits out of it, so the cost reduction and the increase in profitability is the major focus the companies or the startups or any kind of a investment oriented guy is looking at. So it automatically increases in the productivity. So like Kapil was mentioning that he would be able to reduce the carbon footprints by a certain level, 50% to 60%. So definitely a lot of innovative thoughts come up because of this initiatives. Extrinsic drivers are, like I was mentioning, that India itself has signed the Paris Agreement and they have the net zero achievement by 2070. So there are a lot other initiatives which are gradually being undertaken, and the rollout of it is seen that the awareness of carbon market is increasing. BEE has also come out with the standards in which they are proposing to roll out a full-fledged carbon trading system. It's very prevalent in the European countries. So that is also what is happening. So basically, once we are trying to evaluate or put a price to the carbon, so the four tests which it has to meet is the investment. So the proving that the revenue generated from the sales of the carbon credit is essential for the financial viability. So there is where the additionality, this is the first point of it. So once you were mentioning that $50 is the estimated cost which you would require to make it viable, still it would not be able to meet the conventional firing stations, modules. So that is one part of it. So you need to prove that this is very much required to make my technology feasible. And technology is that, like in the e-waste management, that whatever I'm doing would be able to reduce the emissions going on in the longer range. Regulatory, BEE, Ministry of Power, I mean, everyone is coming out with the regulations. India itself has got into certain obligatory obligations. So we have to collectively think and try to get onto a measure how to mitigate all those things. So ultimately, is the common practice that proving the project reduces the greenhouse gas emissions compared to the similar projects that employ common practices. So once we are doing business as usual, we cannot claim carbon credits. You need to do something different. Once we are doing something different and we are able to demonstrate it, that is when the additionality test or it gets cleared, and then only the registries across the globe gives value to the carbon emission which is being actually done. So the compliance market challenges. So there is a baseline which needs to be established, and it has to be proven that there was certain kind of, carbon emissions which were reduced by that kind of a technology rollout. And in the compliance markets, like if BEAD comes out with a obligation that oil and gas has to reduce their emissions come what may, then you may not be requiring the carbon credits to be priced at all. So you'll have to roll out the technology any which way. So that is the beauty of it. So in the compliance, the challenges are the hard to abate sectors like steel, cement, petrochemicals. So it has to be there. I mean, they cannot operate or they cannot manufacture without doing the carbon emissions. Even though if we use the entire power sourcing from renewable, then also the process is such that the carbon emissions would be there. So from there, the additionality or the carbon credits which are getting generated from such unique projects, so like for the e-waste management things, these can be sourced to them, and they can then declare that because of them, this particular investment has actually seen the dawn of the day, and that is the reason they can claim and go back to the auditors and say that this is my investment, this is for because of me, it has been successful. So this is the compliance market. Voluntary market is where the investors have a requirement. So in India, if BEE rolls out the regulations, there would be a certain compliance, target. It could be 40%, it could be 30%, it could be 50%, but they would be seeing at the sensitivity of the industry they are trying to take a decision on. So if I want that everything can be nullified, it cannot be, because if in a process driven industry, there has to be certain areas where you cannot do away without the consumption of the fuel or the carbon emissions. So there, whenever investors come and say that I'm interested, but hey, you will have to take care of the remaining 60% of it, that is where the voluntary market comes into play. So the one when BEE announces that you have to do would be an compliance market, and once the investment or the CSR committee thinks that we have to be net zero by promoting in this new technologies, then the voluntary compliance will come into picture. So what in Tata Power, we have been doing a lot of philanthropic projects. So the rooftop solar, ground mount solar pump, microgrid, and agrivoltaic. Solar pump and microgrid are basically for those uh, clients or the end users who are deprived of the basic necessity of electricity, and they are in the decentralized areas where still the network is not accessible. So there the carbon credits can be generated. So this is one of the things which we are trying to do now. Aggregation of the, I mean, this is explaining the process of it, but seeing that this is a proper technical thing, so I would skip this particular slide. But basically what it is demonstrating is that whenever the additionality test has been demonstrated, we have to take it to certain registry who will actually do the monitoring, verification, and the issuance of it. So you can go to the gold standard, you can go to Vera. So there are multiple registries out there, and this MBETS platform is what we are trying to work on. So this would be a blockchain enabled technology. What we are trying to achieve here is that these are remote locations, and it's not possible for a person to go and verify each and everything manually. So we would be deploying certain kind of IoT enablements there, and whatever the carbon dioxide is being reduced or is being avoided, based on that it will directly being monitored and issued on the platform itself. And it would be, we are trying to get it linked with the certain registries, and once it happens, then the certification would be very easy for them also to issue. So on this platform, what we are hoping to achieve is that the buyers and sellers would come directly on a singular platform, wherein the buyers would be able to state the compliances or the requirements of the obligatory nature or of the compliance nature. And on the other hand, whenever a new technology is getting rolled out, we can help them in getting the carbon credits issued, and putting a fair price to it would be the uniqueness of this platform. So this is what we are trying to bring. So generally, I mean, this is again for the part of it that if we are able to do so, we can have additional saving of around 20 20 paisa per unit. So 1 CR, we are assuming that it could be traded at $2 or $3 currently, which is the ongoing price, thanks to the Russia-Ukraine war. So it's earlier it was going at $20. So if this is what is happening, then we estimate that there would be an additional saving on the cost on the energy savings, as well as on the emission savings. So the strategic benefit of this particular platform which we are trying to say is that we would be prepared for the Indian CCTS to be rolled out, and it would help in deployment of new and better technologies viable. Definitely it would also help in to bring in more brand value to the new startups and the new investment oriented or who wants the investment. So the credibility can be generated by that. It could ease easier funding at a lower interest rate, and there would be a long-term readiness for the compliance market when the targets become more stringent. So this is what the entire construct of it is, which we are trying to bring in. So basically, integration of a small-scale, low-carbon technologies, facilitating by supporting technologies like blockchain, can make India influential in shaping emission reduction strategies, guiding policymakers and stakeholders towards a sustainable future. So that is what we are trying to achieve here. So thank you.
Thank you, Vishal, for your excellent presentation.
Thank you.
Thank you. May I now call upon Sumitra Ghosh for his presentation, please.
Good morning, uh, respected chair, distinguished delegates, and fellow speakers. I'm Sumitra Ghosh. I'm Principal Heat Transfer Engineer with Shell India Markets Private Limited. And in the audience, my co-speaker, Srikant Kumari, is also there. This is a legal disclaimer that whatever we are presenting here have some confidential element into it, and it is related to IP. So please exercise your caution for reproduction. So in this, we'll cover why are we talking about energy transition, what relevance it has for the process industry, what kind of alternate fuels we can fire based on available technologies, and fuel means heat, and that's why we are here. So what kind of heating applications we have in the industry, and how can we get carbon credits or adopt new technologies to reduce the emissions that we have agreed in Paris Protocol. So if you see the large amount of heat required in the industry is accountable for heating the processes. Process means in refinery or petrochemicals, we need to heat up process fluid to get good products, distillates. And out of that, industrial heating, 90% of energy are sourced from fossil fuels. And not only for oil and petrochemicals, it is required all over all the processes. It can be cement industry, it can be metal industry, it can be power industry. Everywhere fuel is the flywheel, and from fuel only we get the energy. And fuel in today's world, in fossil fuel, lot of carbon dioxide, NOx, SOx, which are unwanted, we wanted to reduce. If you see, there are color coded of that whatever energy intensity wise, Red are high temperature heating. Those are hard to abate. What are those sectors that require that high energy? It is power sector and the cement industries, metal industries, or in the refractory industries. And the most important part what we will be focusing on today is that medium heating up to 400 degrees centigrade. And that is also not negligible. That is around maybe around 40% of that is the low temperature heating and medium temperature heating and low temperature heating. So if we see that in today's world, we have around 36.5 gigatons per annum CO2 reduction, which we want to abate to have 1.5 degree centigrade target. So today's technology is not good enough to reach us there. And we have above that growth projections, which is up to 1.7% per up to 2030. So not only we have to reduce in whatever we produce today, also we have to think of how do we maintain our growth strategy. So it is the same thing what that low temperature and medium temperature heating that we'll be talking about. And for the high temperature heating, that is very difficult to abate that CO2 emissions from there. But there also we have a solution because hydrogen fuel is such that it can work in that high temperature heating application as well. So what are the key success factors for energy transition? Cost of renewable power. Right now it is high, but it is not to remain that high in foreseeable future. For example, in 1990s, we had very high cost for solar power. Now today we could reduce that up to 90%. Who knows, in future hydrogen price also will become lower if we try working from today. And then in our energy mix, how much we take from the renewable power, that is also important. It is not possible to have renewable power everywhere in the world. And based on the geographic location and economic sense, we can have a mixed platter where we have economically use and the power which is available at low cost. And if we have a good legislation that we talked about in the previous presentations, we covered about that, then it helps to deploy the new technologies. Because in today's technology, some technologies are maybe nascent and involve a lot of cost. But if we have a good legislation and penalty for CO2 emissions, then those technologies can become viable. And once those technologies become viable, more funds pour in to improve and make it less costly. And then again, it comes to electricity versus gas cost. Nowadays, we burn gas because electricity is costly. But if we get a cheaper electricity and gas price goes high, our economic scenario changes. And we may try to use electricity in more expanded form. And hydrogen supply chain. Nowadays, hydrogen production, maybe we know have technologies, but transportation and storage is still a problem. So if we can reduce the cost for transportation and storage of hydrogen, then it can be used more efficiently. So hydrogen burning technologies are developing. We have a solution there, but getting the supply chain in sync with that technology is yet to come up. Here, if we can see that hydrogen, where do we see hydrogens are beneficial is that hard to abate sectors. For example, it is steel, iron and steel making, building sectors, and then cement industries, metallurgical industries. Their high temperature applications are required. And sometimes where we have renewable power, but that is not very stable. In some part of the day, we have lot of renewable energy available, and some part of the day or season, it may not be available. So to have a switch between the renewable power and the gaseous fuel power, hydrogen can play an important role. And we can interchangeably use hydrogen in those sectors. So when renewable power is not there, we can use hydrogen. That time we can still maintain that zero carbon policies there. And right now, hydrogen is still a costly technology, but we expect beyond 2030, it will become cheaper and we will be able to use it in more and more sectors. Hydrogen is a very special fuel. Kapil mentioned that in his presentation, and good combustion engineers always agree. Why hydrogen is different? It is very small molecule, but it is very powerful indeed. It has very high calorific value in terms of mass. But since it is a very small molecule and uh, very low molecular weight, on volumetric terms, it has very poor heating value. And because of that, volumetric flow of hydrogen requirement for a given heat duty is much higher. That is why we need much higher pressure supply at burner. And that is often problematic because hydrogen is not always available. When we switch from hydrogen to natural gas, that transition is difficult. I'll come to the next slides where I'll explain why it is difficult. And hydrogen, few other problems in furnaces when we use hydrogen as fuel. Hydrogen flames are very difficult to detect. Sometimes it can be seen, sometimes it cannot be seen. Where it can be seen, if it is a dim light outside, it can see it. But when it is exposed to other lights, you cannot see it. Hydrogen detection of flame. What is the flame boundary? For that, for conventional fuels, we use CO probing. But in hydrogen, pure hydrogen, we do not have any CO. So how do we define a hydrogen flame? We need to know how close is the hydrogen flame to the tube. Unless we know what is the flame boundary, how do we protect our tubes? There is a way out, but still that technology is not that everyone knows. We may have hydrogen probing, but those probings are not very very common and it is costly. Then in hydrogen, we, as Kapil also mentioned, this flame temperature is very high and also it requires less amount of air and flue gas quantity is also less. And if that is flue gas quantity is less, then the problem is we will have less heat transfer in the convection section. So my duty will shift from convection to radiant. So retrofit will be difficult if we do it existing furnace and we want to fire hydrogen in it. And flame transition, I said that natural gas flame is very blue, bright, but if you go for hydrogen, it has become yellowish. And the flux density also changes. The hydrogen flames are very easy to catch. So that is why the flame high heat flux density is towards the burner, towards the lower section of the firebox. And the NOx, one thing I must tell that NOx is increasing, but at the end we see NOx is actually decreasing than what we expect. Why it is so? Because at that end, prompt NOx production is less. Prompt NOx is facilitated by presence of hydrocarbons, but when we don't have hydrocarbon, we don't have prompt NOx formation. That is why there is a reduction. That is defined by a red curve decline. So this I already discussed. In the view of time, I can skip it. The one thing I must tell that OB index is a measure of how much heat we can send from an existing orifice. So if we have a fixed OB index of a gas, so for a given orifice size, even if my gas composition changes, then same amount of heat can be transferred we can get same amount of heat in the burners. So around 5% of OB index variation is possible in a given orifice. So if you see that OB index band, if we use a band towards top of the curve, then that will not cover my 100% hydrogen. So if a burner is designed for 100% methane, it can cater to around 30-40% hydrogen, but it will not be suitable for 100% hydrogen. On the other hand, if we select a band towards the end, it is suitable for 100% hydrogen, but it will not be suitable for 30% or 20% methane. So that is why interchangeability is difficult. Radiative heat transfer, as Kapil also mentioned, that in conventional furnaces we use flames for radiative heat transfer. But here what we do, there is no flame. In the firebox panels, we replace the panels with electrically heated wires. And those
Hello.
radiative wires are transferring heat to the tubes
Hello, hello.
through which we
Ara,
pass process fluids.
sayonara.
What is the
Arigato.
advantage here? Because electricity is very easy to control. Unlike flames, where we have flame impingements, we have hotspots, here hotspot control is very easy. What is the difficulty? Supply chain. We do not have many vendors who can supply and construct this kind of heaters. This technology is new. Advantage, it can have very high efficiency because in conventional fired furnaces, there is a loss in flue gas, but here there is no loss. I think same thing is mentioned here. In view of time, we will not skip it. The other thing is convective heater. This is nothing but a kind of shell and tube heater. So in the shell and tube, through the tube, we pass hot fluid or cold fluid. But here, tubes are replaced by electrically heated wires, which are insulated in MGO packings and then covered in a metallic sheath. The challenges here is, in conventional exchangers, my hot side temperature is fixed by the hot inlet temperature. But here there is no such control. We can have infinite heat provided the conductive resisting wire can carry it. So that is the problem. If we do not have good heat transfer in the shell side fluid, we may develop hotspots, and there are coke-prone services or thermally sensitive services. For there, in those applications, these kind of heaters may not be suitable. So how we control the cell side heat transfer and flow pattern, that is important. If we have a good kind of flow profile, using the helical baffle or good velocity profiles in shell side, then we can get rid of hot spots. And there are other electrical disturbances, for example, panel heating and maybe formation of hot spots and the leakage currents. Those are points of bad reliability. If we have those problems, then we may plant may trip and we can lose the entire unit. So in summary, how can we achieve energy transition very in a good economic manner is that we improve the energy efficiency. We can do that by using electricity and hydrogen to some extent. Use of low carbon energy. So is it either it can be green energy or it can be hydrogen. Carbon sinks. If we have fossil fuel, we can still capture that CO2 and fix it. And with good policies like high carbon penalties and the government policies. That's all. Thank you.
Thank you, Sumitra, for extensive presentation. With this, we are at the end of the session, and I'd like to thank all the audience for active participations in this question and answer sessions. I would also like to thank my speakers for properly addressing the questions. Thank you all. Thank you.